In this tutorial, we're going to be talking about exponential functions, just like the one that describes the growth of this bacterial culture. In 3.5 specifically, we're going to be talking about transforming these exponential functions. So first off, let's just graph these three functions. We have f at x, which is equal to 2 to the power of x. G at x has the same base function, except we're going to add a c value. And then h at x is the same base function again, except we're going to subtract a c value. So we fill in each of the table of values in order to graph, and we do that by subbing in the x values into your exponent, and then whatever this equals to, that becomes your y value. So I figured out all the y values already, and then I've even graphed them for you. Okay, so we have our f at x, that's this one, our original. Then if we added 4, we get our g at x, which is orange. And if we subtract 3 from the original, we get the purple, and that was our h at x. So if we're going to transform f at x to g at x, we notice that if the c value is positive, that's just my short form for positive, the graph goes up. If f at x transforms into h at x, the c value was a negative, and therefore the graph goes down. So if we take a look at the asymptotes, we notice that the same is true for the asymptotes. When c was positive, the entire graph went up, which means that the asymptote also went up. In this one, c was negative, so the asymptote went down with the rest of the graph. Here are three new functions. So we have f at x, g at x is very similar, but you have this a value now. And then h at x, again very similar, but a different a value. So what we're going to do is we're going to graph each of these and compare, because we're changing the a value now. We need all of our y values, and then we're going to graph. Here's our f at x, our g at x, and then our h at x. So when f at x transforms into g at x, we have to remember that in this case our a was 3. Because of that, it's going to be a vertical stretch by a factor of 3. So if you take a look at this guy, it's going to be stretched vertically, and that's why it became a little bit steeper. Then if we have our f at x and we transform it into the h at x, this guy had an a value of 0.5. That was between 0 and 1, and therefore gives you a vertical compression by a factor of a half. And that's why when you have your f at x, it then transforms into something that's a little bit less steep. You may have noticed that each of the asymptotes was not affected by your a. Your vertical stretch or compression will have no effect on where the position of your asymptote will end up. All of them will be exactly the same as your f at x. So let's just sum up. If we have the original exponential function and we start transforming it, so for instance adding an a value, it's going to stretch it vertically or compress it vertically. Now if your a is a negative, it's going to be a vertical reflection, in other words a reflection in the x-axis. Now your c value is a vertical translation, which means it's going to move your exponential function up and down. Since these are the same types of transformations we've seen compared to other functions, why don't we just add the rest in? Your k value, that's your horizontal stretch or compression, and remember if it's a negative, you're going to get a horizontal reflection. So that means that your graph is going to reflect over the y-axis. Then we also have our left and our right, so that's our horizontal translation. Okay, so all of these are the same types of transformations that we've applied to quadratics, reciprocal graphs, and so on. We're just applying them now to an exponential graph. So let's give you a very quick example. Here are all the different transformations in one equation. So it looks like the base equation is 2 to the power of x. This is going to be a reflection, and it's a vertical reflection, so that means it goes over the x-axis. We have this little 2, which was our k value, that is our horizontal compression, okay, because remember it's the opposite of what we would think. It's not a stretch, it's going to be the opposite, which is a factor of 1/2. Okay, and then we have the -3, that means that we're going to the right 3, and then we're also going up 5. Okay, so what we're going to do is we're going to do, whether you do reflections or stretches and compressions first, it doesn't matter. So why don't we do the original graph, y equals 2 to the power of x, then the stretch or compression, okay, and the reflection. Then we have the moving to the right 3 and then up 5. Okay, so those are all of the transformations put into one, and again, there is a certain order to them. Also notice where the position of certain key, characteristics are. So for example, you want to keep in mind domain and range, you want to keep in mind the asymptote, and also any intercepts.